Hello dear students, welcome you all. In this lecture, I am going to discuss about the next type of analog to digital converter, and this is counter type analog to digital converter, right? You know very well that in the previous lecture, I have discussed about the first type of A to D converter, and that was a simultaneous conversion from analog to digital, or we can say it was a flash converter, right? But in that converter, although it was very simple to design and execute, there was a major problem, major drawback. The drawback was the requirement of 2 raised to power n minus 1 number of comparators, right, where n is the number of bits required in the corresponding digital signal. So as the number of bit required in the signal increase, then the requirement of the comparators increase. So in that case, I told you in that lecture also, it become very difficult to design that circuit and then arrive at an encoding matrix, encoding equations. So this problem is removed in this counter type analog to digital converter, and this converter make use of only one comparator. You can see here. But in addition, it requires some additional circuitry that you can see here. The heart of this entire counter type A to D converter is the n bit counter. You can see here, it is placed here. It is n bit counter, right? N bit, where n stands for the number of bits that we expect in the output, digital output. So that's why we call it as a n bit counter. So you can see here, this circuit consists of an n bit counter. This is a digital to analog converter. Now, this is the reason I have discussed D to A converters first. Then I am going for A to D converters. I have told you at that time also that D to A conversions is easy as compared to A to D conversions, and also D to A converters form an integral part of A to D converters also. So you can see here, D to A converter is used here, and you know very well that we have two type of D to A converters, either resistive divider, right, or binary ladder network. So we can say that binary ladder network is used for D to A conversions, right? So whatever output we are getting from the counter, that is applied to the ladder network D to A converter. Then the output of D to A converter is sent to the one input of the comparator, and it is inverting input, negative. Whereas this output of the counter is also applied to the latch. Latch means flip-flop, registers, shift registers for the storage of this digital output, right? This is a control circuit that is used for controlling, right, and generating clear, right? It is an AND gate, it is a clock signal, right, and the analog signal that we are going to convert into digital signal that is applied on this terminal, non-inverting terminal of a comparator, right? Now you can see this table, right? You can see this table. I am showing you it. Now you look at this table. Suppose we want 3 bit, right? 3 bit in the digital output, right? Then obviously we will need 3 bit counter, right? And in case of 3 bit counter, we know what are the different possibilities, starting from 0, 0, 0, 0, 0, 0, 1, then all we have total 8 possibilities, right? So 8 counts will be made by this 3 bit counter starting from 0, right? Now when we apply the clock pulse here, in order to understand the working of this entire circuit, suppose initially the counter is cleared by using a clear pulse by this control circuit, right? So initially the output of the counter is 0, right? 0, 0, 0 means the output is, so that output is applied to D to A converter. Obviously the corresponding analog voltage to this 0, 0, 0 signal will be 0 volt, and that is applied to the comparator. Now if we look at the comparator, at that time the input at this terminal is higher as compared to this one, so obviously the output of the comparator will be in a positive saturation. We can say it is high, but right, when it is high, it is applied to the AND gate. Now, and at the same time, this is also applied to the control circuit. When this is high, it is also going here to the control circuit. Now this, when one is applied at the AND gate, it means now if we send a clock pulse, right, at the other input of the AND gate, that clock pulse will be passed to the counter, and the counter will begin counting starting from the 0, 1, 2, 3, 4, 5, 6, 7, right? It will keep on counting, and whatever counts are generated, these counts are applied here. You can see here to the digital to the analog converter. And what is the output of this D2A converter? It will be this kind of staircase waveform starting from 0, 1, 2, 3, 4, 5, 6, 7, so on, right? So we will have this staircase waveform or rising ramp, right? Digital ramp, A to D conversions, right? Now this digital to analog conversion of the corresponding signal is this, right? And this signal is sent to the this side, right? So as I told you that when this ramp voltage, rising ramp, becomes either equal to or greater than this B input. Now very important, when it goes equal to or greater than B input, at that instant, what will happen? The output of the comparator will change its state. We know very well comparator is comparing the two inputs. It will change its state, and now its state will go low, right, from high to low. And when it goes low, now this low is applied here. When it is low, it is immaterial. Low means it is 0, then it is immaterial whatever input we are applying at the other terminal of the AND gate. The output will always be low or 0. And at that instant, the counter will stop counting, right? At the same time, this 0 is sent to here control circuit, and this control circuit will send a signal to the register, and whatever information was present in register or latch at that time, that information will be holded, latched, locked, right? And the control circuit will send a signal at that time to the counter and make it clear. Make it clear means it will set the counter back to the 000 position. So this will complete one conversion, right? Suppose the output of the DAC at that time was 3 volt, suppose, right? Then that 3 voltage will appear here, and then that 3 volt will become, suppose it was 2.9. Then at that time 3 is more than 2.9. This will generate 0, 0 will go there, counter will stop, right, and latch will hold 3 volt. So that will be the corresponding output, digital output corresponding to that 2.9 volt input, right? So that information 3, that will be holded, right, in this latch, and that will be the corresponding output for the given analog input, right? And now when this conversion is complete, then this clear signal is given to the counter, and counter is once again set to 0, and then it will again start counting. It will again start comparison. So then it will keep on comparing till the this input becomes greater than this. Then the next conversion will be complete. So in this way, the analog signal will be converted into corresponding digital signal. I have shown you the table for this, right? But here one thing is very important, right? That here we have taken 8 levels, and the maximum value is you can see here 111, it is 8 volt, we can say, right? Sorry, 7 volt. If we are taking reference volt, 1 is equal to 7 volt. Then in that case, now when we are doing the conversion, then the peak to peak voltage for this should be 7 volt. Because in that case, it can't proceed further 7 volt. So maximum value available in the input analog voltage should be either 7 or less than 7. So depending upon the bit requirement and the given voltage, we can make these adjustments, right? So this is the way of working. This is the staircase waveform that I got from this ladder network, output of digital to analog converter. We call it as a digital ramp ADC, right? That ADC means it is given to the ADC circuit, right? This ramp is given to the analog to digital conversion circuit, right? Now look at this graph. You can see here this is the input, right? And this is the conversion, corresponding conversion. So suppose the counter start from here from 0 and it reached at this point. Now at this point the ramp voltage try to go beyond input voltage, whatever I said here. It now want to go more than this, and at that time the bit was now it is the case of 4 bit, right? I have taken the case of 3 bit. So at that time the bit that the bit stream that was present as the output of counter was 1000. Now at that time this information will be stored in the register and the counter will be sent back to the 0 position. Then it will again start counting and take the next sample, right? So in this way samples are taken. You can see here. Now it is very important from this graph that the time of resolution means the time required for the counter to take samples. It is quite large. This is the time, right? Now every time the counter is starting from 0, this is a drawback, right? It won't be able to take the large number of samples in the given time, because every time it is starting from 0. You can see here in all these cases. So this is a major drawback of this counter type A to D converter, right? These samples will be the samples of the corresponding analog voltage, right? And we can say it will be the converted format of A to D, right? Now I am coming to the resolution time, right? Resolution time, right? So as I am saying the resolution time, resolution of the DAC will be defined as the number of bits generated in the binary output, right? If we are having 8 bits, then we can say that it has 8-bit resolution. If it had 4 bits, then we will say it will have a 4-bit resolution. Similarly 16 bits, 16-bit resolution. Now the time for getting the 16-bit in the output, that time is known as the resolution time. And how we can calculate that time? Now as I told you that the time of conversion, this time, right, it depends upon the this sequence, because every time the counter will begin from 0. Now if we are using 3 bits, right, then when it begins from 0, what is the maximum time that counter can take? The maximum time that I call worst time, right, that will happen when this will have a 6.9 volt, because it is the 7 volt is the last. If I am taking 111 as a 7 volt, 7 volt is the last or maximum value that corresponds to 111. So this is the maximum value, right? So the maximum time, right, that required for the conversion, I call it as T conversion maximum, that will be equal to 2 raised to power n, right, multiplied by T clock, because T clock is the time for 1 clock pulse, because with every clock pulse the counter is advancing 1 step, right? Like this is 0, 1, 2, so on. So the T clock is the clock time of a 1 clock pulse, right? So if we have 7, right, this in the output, right, then I will say that this clock time, the time of conversion required will be 2 raised to power n multiplied by the time of 1 clock, right? If I talk about the average time, then I have to divide it by 2. So in that case, this T C maximum average, that will become 2 raised to power n minus 1 into T clock. So this is the time that must be spent at least in order to have a conversion from A to D, right? So you can see here that the maximum time that is required for the conversion, it is 2 raised to power n into t clock, and the average time, right, that is 2 raised to power n minus 1 into t clock, right. So if I want more resolution, because the resolution time, right, it depend resolution of the counter depend upon this time. If I'm increasing the number of bits in the stream, then the time that is required, because it depends upon the number of bits, right, it will also increase. So there is always a trade-off between the number of bits required and the resolution time, right. We can't increase the number of bits in arbitrary manner, right, because that will pose another kind of challenge, that is the resolution time, or the time required for the maximum value of the signal, maximum voltage of the signal, and that will correspond to like the highest possibility of the counter, right. So this is the main drawback of this counter. So this drawback can be removed if every time counter does not start from 0, but it starts from some other value that is very close to this one. So this drawback was removed in next type of A to D converters, but still this converter, counter type A to D converter, is quite efficient in doing the A to D conversions as compared to the flash converter, right. So this is all about the A to D converter. So thank you very much.